Welcome to Slumbertainment. Get comfortable, close your eyes, and let yourself relax. Tonight we explore the history of agriculture. Please like and subscribe for more restful content. Now, let's begin. The transformation began quietly in scattered pockets across the world, roughly 12,000 years ago. For millions of years before this moment, human beings had moved with the seasons, following herds of animals and gathering what grew wild. Then something shifted. People began to notice patterns in the plants they collected, the way seeds fell to earth and sprouted in familiar places, the rhythms of growth and harvest that repeated year after year. This awareness marked the beginning of agriculture, though those early practitioners would not have recognized the word or understood the magnitude of what they were initiating. The change happened independently in at least 7 different regions across the globe. In the Fertile Crescent, that arc of land stretching from the Persian Gulf through modern Iraq and Syria to the eastern Mediterranean, people began cultivating wheat and barley. In China, communities along the Yellow River and Yangtze River developed rice and millet farming. In Mesoamerica, maize, beans and squash became the foundations of settled life. The Ethiopian highlands saw the domestication of teff and coffee. New Guinea's highlands produced independent agriculture based on taro and banana. The eastern United States gave rise to farming centered on squash, sunflowers, and a now extinct grain called goosefoot. And in the Sahel region of Africa, people cultivated sorghum and African rice. Each of these centres developed farming without knowledge of the others, suggesting that agriculture was not a single invention, but rather an idea whose time had arrived in multiple human societies simultaneously. The mechanics of early farming were deceptively simple. People saved seeds from plants that produced larger grains or fruits, inadvertently selecting for traits that made crops more suitable for cultivation. Wild wheat, for instance, had seed heads that shattered easily, scattering seeds across the ground as a survival strategy. But farmers preferred plants whose seeds stayed attached to the stalk until harvest, making collection easier. Over generations, this preference transformed wild grasses into domestic crops. The same process occurred with animals. Wild sheep were nervous, rangy creatures. Domestic sheep, bred over centuries, became docile and grew thick wool. Wild cattle were aggressive and lean. Domestic cattle grew larger and calmer, better suited to work and milk production. This process of domestication required patience measured not in seasons but in centuries. Each generation of farmers made tiny adjustments, saving seeds from the most productive plants, breeding animals with desirable traits. The changes were so gradual that no single person could have perceived the transformation taking place. Yet over 1,000 years, 2,000 years, the landscape itself began to change. Forests were cleared to make room for fields. Rivers were diverted to water crops. Wild ecosystems gave way to human-managed environments organized around the production of food. The implications of this shift were profound. Hunter-gatherer groups remained small, mobile, and egalitarian by necessity. Agriculture allowed, and eventually required, people to stay in one place. Permanent settlements appeared, first as small villages, then as towns. When you plant a field, you must remain nearby to tend it, to protect it from animals and competitors, to harvest what grows. This permanence created new possibilities and new problems. Surplus food could be stored, allowing populations to grow beyond what wild resources could support. But stored food attracted pests and required protection. Social hierarchies emerged to manage the distribution of resources. Some people farmed while others specialized in crafts, trade, or administration. The division of labor, one of the defining features of civilization, arose directly from agriculture's ability to produce more food than the farmers themselves needed to survive. The earliest farming techniques were learned through observation and experimentation. Farmers noticed that certain plants grew better in particular soils or seasons. They discovered that breaking up the earth before planting improved yields, leading to the development of simple digging sticks and eventually ploughs. They learned that some crops depleted the soil while others seemed to restore it, though they did not yet understand the chemical processes underlying these patterns. Legumes, such as peas and lentils, have root systems that host bacteria capable of converting atmospheric nitrogen into forms that plants can use, essentially fertilizing the soil. Ancient farmers did not know about nitrogen fixation, the scientific term for this process, but they recognized that planting beans one year made the next year's wheat crop more productive. Water management became crucial early in agriculture's development. Rainfall alone was unpredictable and often insufficient. Communities near rivers began digging channels to direct water into their fields, creating the first irrigation systems. In Mesopotamia, farmers developed extensive canal networks that transformed arid land into productive cropland. These systems required coordination and maintenance, spurring the development of centralized authority and record keeping. Someone had to decide how water would be distributed, settle disputes, and organize the labor needed to maintain the canals. Clay tablets from ancient Sumer, some of the earliest writing in human history, record grain quantities, land allocations, and water rights. Agriculture and literacy emerged together, each supporting the other's development. The tools of early farming were simple but effective. Wooden ploughs, sometimes tipped with stone or bone, broke up soil more efficiently than digging sticks. Sickles made from flint chips set into wooden or bone handles allowed farmers to harvest grain more quickly. Stone grinding wheels turned grain into flour. Each innovation increased productivity, allowing farmers to cultivate larger areas and feed more people. Yet these tools also bound farmers to their land. Unlike hunter-gatherers who could move when resources diminished, farmers had invested labour in clearing land, building irrigation systems and improving soil. Abandoning a farm meant losing that investment. This created a new relationship between humans and place, a rootedness that would shape societies for millennia. The adoption of farming was not universally beneficial to the individuals who practiced it. Studies of ancient skeletons reveal that early farmers were often shorter and less healthy than their hunter-gatherer ancestors, likely due to less diverse diets and the new diseases that emerged in permanent settlements. Yet farming communities grew faster and could support larger populations than mobile groups. When resources became scarce, farming societies could often outcompete hunter-gatherers through sheer numbers. Agriculture spread not necessarily because it made life better for individuals, but because it made societies more populous and, in conflicts over land and resources, more powerful. This pattern would repeat throughout history as agricultural techniques evolved and intensified, each innovation bringing both benefits and costs, transforming not just how people ate, but how they lived, organized themselves, and understood their place in the world. As agriculture became established, farmers confronted a fundamental challenge that would occupy their attention for thousands of years: soil fertility. A field planted with the same crop year after year gradually produces less. The plants extract nutrients from the soil, particularly nitrogen, phosphorus, and potassium, and without replenishment, yields decline. Early farmers observed this phenomenon without understanding its chemistry. They knew only that new fields were more productive than old ones, that certain practices helped maintain yields, and that ignoring the problem meant hunger. The earliest solution was simply to move. Slash-and-burn agriculture, practiced independently across tropical and temperate regions, involved clearing forest or brush, burning the vegetation to release nutrients into the soil, farming the land for several years, then moving on when productivity declined. The abandoned fields would gradually revert to forest, and after a decade or two, the cycle could begin again. This system worked well when populations were small and land was abundant. The burning released nutrients locked in plants back into the soil, providing a temporary boost of fertility. The ash itself acted as fertilizer, rich in minerals that crops needed. But as populations grew and available land diminished, the intervals between clearing and re-clearing shortened. Fields had less time to recover. Soil erosion increased. What had been sustainable at low population densities became destructive under demographic pressure. Farmers in regions with less abundant land developed more permanent solutions. In China, as early as 4,000 years ago, agricultural texts describe sophisticated approaches to maintaining soil fertility. Farmers learned to apply human and animal waste to fields, returning nutrients to the soil in a closed cycle. This practice, which Western observers would later call night soil fertilization, involved collecting human excrement from cities and villages and distributing it to surrounding farms. The system was efficient and effective, though it required careful management to prevent disease transmission. Chinese farmers also developed systems of composting, mixing plant waste, manure, and soil to create nutrient-rich amendments. These techniques allowed continuous cultivation of the same fields for centuries, something that would have been impossible without deliberate fertility management. The concept of crop rotation emerged from similar observations about soil depletion and restoration. Farmers noticed that following a grain crop with legumes improved subsequent harvests. In the Mediterranean region, a two-field system became common. One field planted with wheat or barley, the other left fallow, meaning unplanted, to recover. The fields would switch roles each year. This approach sacrificed half the potential production at any given time, but maintained long-term productivity. In Northern Europe, a three-field system evolved during the medieval period, dividing land into three sections. One field grew winter crops like wheat, another grew spring crops like oats or barley, and the third lay fallow. Each year the fields rotated through these three states. This system increased production compared to the two-field approach while still allowing soil recovery time. The science behind these practices would not be understood for millennia, but the observations were accurate. Legumes host bacteria in their root nodules that convert atmospheric nitrogen into ammonia, a form plants can absorb. When legume roots decompose, they release this nitrogen into the soil, effectively fertilizing it. Fallow periods allowed natural processes to restore nutrients and break pest cycles. Weeds growing in fallow fields were often deep-rooted, drawing minerals from lower soil layers and concentrating them near the surface when the plants died and decomposed. Farmers did not need to understand the mechanisms to benefit from them. They needed only to observe results and transmit successful practices across generations. Animal integration became another crucial element of sustainable farming. In many agricultural systems, animals and crops formed complementary relationships. Cattle, sheep, and goats grazed on fallow fields, and crop stubble, their manure fertilizing the soil while they consumed plants that would otherwise go to waste. Oxen and water buffalo provided labor for ploughing, allowing farmers to cultivate larger areas more efficiently. In rice-growing regions of Asia, ducks and fish were introduced into paddy fields. The ducks ate insects and weeds while their droppings fertilized the rice. Fish consumed mosquito larvae and added nutrients to the water. These integrated systems maximized productivity while maintaining ecological balance. The plough itself underwent significant evolution during this period. Early ploughs were simple wooden implements that scratched shallow furrows in the soil. They worked adequately in the light, dry soils of the Mediterranean and Middle East, but struggled in the heavier, wetter soils of northern Europe. Around the 6th century, farmers in northern regions developed the heavy plough, equipped with iron blades and wheels. This implement could cut deep furrows, turning over thick sod and clay. The heavy plough required substantial animal power, typically teams of 6 or 8 oxen, which meant farmers often had to cooperate, sharing equipment and draft animals. This cooperation influenced settlement patterns and social organisation. Villages became more cohesive, with common fields and shared labour obligations. The mouldboard plough represented another refinement. Earlier ploughs simply cut into the earth. The mouldboard, a curved surface attached to the plough blade, actively turned the soil over, burying weeds and crop residue while bringing fresh earth to the surface. This deeper cultivation improved drainage in wet climates and better mixed organic matter into the soil. The mouldboard plough became standard in medieval Europe and remained in use, with minor modifications for more than 1,000 years. Terracing emerged in mountainous regions where flat land was scarce. Farmers in the Andes, the Himalayas, the Philippines, and the Mediterranean carved horizontal platforms into steep hillsides, creating level fields where crops could grow. Stone walls retained the soil, preventing erosion. Water management systems directed runoff from upper terraces to lower ones, maximising the use of rainfall in dry climates. Terraced agriculture was labour-intensive to establish, but allowed farming in terrain that would otherwise be unusable. Some terrace systems built thousands of years ago remain productive today, testimony to the engineering skill of early farmers and the durability of well-designed agricultural infrastructure. These advances in farming technique were not merely technical achievements, they represented accumulated wisdom, passed down through generations, refined through countless experiments and observations. Each innovation allowed larger populations to be supported, which in turn increased the labour available for further agricultural improvements. The relationship between population and farming intensity created a feedback loop that would drive agricultural development for millennia, pushing farmers to extract more production from each unit of land, to manage resources more carefully, and to develop increasingly sophisticated understandings of the natural processes that govern their harvests. Water has always been agriculture's most critical constraint. Rainfall arrives unpredictably, concentrated in seasons that may not align with growing cycles. Rivers flood and recede according to distant weather patterns. Groundwater lies hidden beneath the surface, accessible only through great effort. The civilizations that mastered water management gained tremendous advantages, transforming deserts into gardens and supporting populations that would have been impossible through rain-fed agriculture alone. The earliest irrigation systems were simple diversions. Farmers dug channels from rivers to nearby fields, allowing water to flow when needed. But as societies grew more complex, so did their hydraulic engineering. In ancient Mesopotamia, between the Tigris and Euphrates rivers, farmers developed extensive canal networks that stretched for miles. These canals required constant maintenance. Silt accumulated and had to be cleared. Breaches needed repair. Flow rates demanded adjustment based on crop needs and water availability. Managing these systems required organisation beyond what individual farmers, or even single villages, could provide. Central authorities emerged partly to coordinate irrigation, and in doing so, gained power over the agricultural production that sustained entire populations. The Nile River created different opportunities and challenges. Unlike Mesopotamian rivers, which could flood unpredictably and destructively, The Nile flooded with remarkable regularity each year, depositing nutrient-rich silt across the floodplain. Egyptian farmers developed basin irrigation, dividing the floodplain into sections surrounded by earthen walls. When the annual flood arrived, water and silt flowed into these basins and remained there as the flood receded, slowly soaking into the soil. Seeds were planted directly into the wet earth. This system required relatively little effort compared to canal irrigation and provided natural fertilization through the deposited silt. Egyptian agriculture became remarkably productive, supporting one of history's most enduring civilizations with a level of food security unusual in the ancient world. In the Indus Valley, farmers constructed sophisticated drainage systems alongside irrigation channels. The monsoon climate brought intense rainfall concentrated in specific months, and managing this water required infrastructure to prevent flooding while capturing moisture for use during dry periods. Archaeological evidence from sites like Mohenjo-Daro and Harappa reveals carefully planned cities with drainage systems that would not be matched in Europe for thousands of years. The agricultural systems supporting these cities likely included reservoirs for water storage, canals for distribution, and careful attention to drainage to prevent soil waterlogging and salinization. Salinization presented a persistent problem in irrigated agriculture, particularly in hot, dry climates. When irrigation water evaporates from the soil surface, it leaves behind dissolved minerals, primarily salts. Over time, these salts accumulate to concentrations that become toxic to most crops. Ancient texts from Mesopotamia document declining yields and the gradual shift from wheat cultivation, which is relatively salt sensitive, to barley, which tolerates salt better. This shift provides evidence of increasing salinization across southern Mesopotamia. Eventually, some regions became too saline for agriculture altogether, contributing to the decline of civilizations that had flourished there for centuries. The lesson was harsh. Irrigation could dramatically boost productivity in the short term, but without proper management, it could also destroy the land's productive capacity permanently. Chinese farmers developed different approaches suited to their environment and crops. Rice cultivation requires flooded fields or paddies for much of the growing season. Managing water for rice is different from managing it for wheat or barley. Paddy fields must be carefully levelled so water distributes evenly. Low walls or bunds surround each paddy to contain water. Systems of channels bring water from rivers or streams, and gates control the flow into individual fields. During the growing season, farmers maintain shallow standing water. As harvest approaches, they drain the field so the ground can dry enough for workers to enter and cut the rice. This system requires enormous labour to establish and maintain, but produces exceptional yields. A well-managed rice paddy can support far more people per acre than wheat fields, which partly explains Asia's ability to sustain large, dense populations throughout history. The Qanat system, developed in Persia around 3,000 years ago, represents one of the most ingenious irrigation technologies ever devised. Qanats are underground channels that tap into groundwater in foothills and transport it to lower elevations through gravity flow. The channels run underground to minimize evaporation, with vertical shafts spaced along the route for construction access and maintenance. Building a qanat required extraordinary skill and effort. Workers dug the vertical shafts first, sometimes reaching depths of more than 100 feet to reach the water table. Then they tunneled horizontally to connect the shafts, maintaining a precise gradient so water would flow steadily without eroding the channel. The system was dangerous to construct, expensive and time-consuming, but once completed, a qanat could function for centuries with minimal maintenance, providing reliable water in climates where surface sources were scarce or seasonal. The technology spread across the Middle East, North Africa, and Central Asia. In some regions, qanats remain in use today, still supplying water to farms and communities thousands of years after their construction. The qanat represents a particular approach to environmental challenge. Rather than trying to dominate or dramatically alter nature, it works with natural processes, using gravity and groundwater flow to achieve human purposes with minimal ongoing energy input. In the Americas, agricultural civilizations developed distinct irrigation approaches suited to their environments. In the coastal valleys of Peru, farmers built canals that brought water from mountain rivers across desert plains. Some of these canals stretched for dozens of miles, following carefully engineered routes that maintained gentle gradients across varied terrain. In the southwestern United States, ancestral Puebloan peoples developed irrigation systems fed by small streams and rainfall runoff, supporting agriculture in one of the continent's driest regions. Their systems included check dams to slow water flow, terraces to capture runoff, and canals to direct water to fields. When climate patterns shifted and droughts became more frequent and severe, these systems proved insufficient, contributing to the abandonment of major settlements like those at Chaco Canyon. Water management shaped not just agricultural productivity, but also social structures, settlement patterns, and political organization. Communities dependent on shared irrigation systems had to cooperate, establish rules for water distribution, and maintain infrastructure collectively. This cooperation created social bonds and power structures that extended beyond agriculture into all aspects of life. The farmer who controlled water access wielded enormous influence. The society that managed water well could flourish even in challenging environments. The civilization that neglected its irrigation infrastructure faced decline regardless of other strengths. Water, more than land or labour, determined agricultural success throughout much of human history. The exchange of crops and animals between regions represents one of the most consequential processes in agricultural history. For thousands of years after agriculture began, each region remained relatively isolated, working with the limited palette of plants and animals that could be domesticated locally. Then, gradually at first and later with increasing speed, these biological resources began to move. Trade routes carried seeds alongside silk and spices. Migrating peoples brought their crops to new lands. Empires spread their agricultural systems across conquered territories. Each transfer created opportunities and challenges, reshaping landscapes and diets in ways that would prove irreversible. The Silk Road, that network of trade routes connecting China to the Mediterranean, served as a conduit for agricultural exchange. Wheat moved eastward from the Middle East into China. Rice travelled westward, though it would not become a major crop in Europe until much later. Fruits such as peaches and apricots, originally from China, reached Persia and eventually the Mediterranean. Grapes moved east from the Caucasus region. Cotton spread from the Indus Valley into both eastern and western destinations. With each crop came knowledge of cultivation techniques, irrigation requirements, and processing methods. Agricultural knowledge travelled as seeds travelled, carried by merchants, pilgrims, and soldiers who observed foreign farming practices and recognized their potential value. The Islamic Golden Age, spanning roughly from the 8th to the 14th century, accelerated agricultural exchange across a vast territory stretching from Spain to Central Asia. Arab and Persian agronomists compiled extensive agricultural manuals that documented crops and techniques from across this region. These texts described irrigation methods, crop rotation systems, grafting techniques for fruit trees, and the properties of different soils. The translators and scholars of Baghdad, Cairo, and Cordoba preserved Greek and Roman agricultural knowledge while adding observations from Indian, Persian, and local sources. This synthesis created a body of agricultural science more comprehensive than anything that had existed before. During this period, crops that had been confined to specific regions spread widely. Citrus fruits, originally from Southeast Asia, became established in the Mediterranean. Sugarcane, first cultivated in New Guinea, moved through India and Persia before reaching North Africa and Spain. Hard wheat varieties from North Africa proved better suited to dry climates than the soft wheats previously grown in southern Europe. Rice cultivation expanded into southern Europe and new regions of the Middle East. Cotton production increased dramatically as spinning and weaving technologies improved. Each of these transfers required adaptation. Farmers had to learn when to plant in climates different from the crop's place of origin, how much water to provide, which pests to guard against, and how to modify local soils to suit foreign plants. The Columbian Exchange, beginning in 1492 with European contact with the Americas, dwarfed all previous transfers in scale and impact. The Americas and Afro-Eurasia had been biologically isolated for at least 15,000 years, developing entirely separate suites of domesticated plants and animals. When these biological systems suddenly reconnected, the consequences transformed agriculture on both sides of the Atlantic. From the Americas to Europe, Africa and Asia came maize, potatoes, sweet potatoes, tomatoes, peppers, cacao, vanilla, tobacco, and numerous bean varieties. These crops would reshape diets and demographics worldwide. The potato particularly proved revolutionary. Native to the Andes, potatoes thrived in climates too cold or wet for wheat. They produced more calories per acre than grain crops and required less labour to cultivate. When potatoes became established in Europe during the 17th and 18th centuries, they enabled population growth in regions that had struggled to feed themselves with grain alone. Ireland's population doubled in the century after potatoes became the staple crop. Similar patterns occurred across northern and eastern Europe. The dependence on this single crop created vulnerability, as the Irish potato famine of the 1840s would tragically demonstrate. But before that catastrophe, potatoes allowed millions to survive who could not have been supported by traditional European agriculture. Maize spread even more widely than potatoes. It grew well in warm climates and produced abundant yields. In Africa, maize supplemented and sometimes replaced traditional grains like sorghum and millet. In China, maize cultivation expanded into marginal lands unsuitable for rice. In southern Europe, maize became a staple, particularly for rural populations. The adaptability of maize to different climates and growing conditions made it valuable across an enormous range of environments. From Afro-Eurasia to the Americas came wheat, rice, barley, coffee, sugarcane, bananas, and crucially, large domesticated animals. The Americas had no horses, cattle, pigs, sheep or chickens before European contact. The introduction of these animals transformed American agriculture fundamentally. Cattle and horses provided labour for ploughing and transportation. Their manure fertilised fields. They converted grass into meat, milk and leather. The agricultural systems that developed in the Americas after contact often hybridized indigenous crops with European animals and techniques, creating new forms of farming distinct from either parent tradition. Sugarcane cultivation in the Americas became one of the most consequential agricultural developments in history, though for tragic reasons. Sugar had been a luxury product in Europe, expensive and rare. The tropical climates of the Caribbean and Brazil proved ideal for sugarcane. European colonizers established vast plantations, but the work was brutal and deadly. The indigenous populations, already devastated by disease, could not or would not provide sufficient labour. This labour shortage led directly to the transatlantic slave trade, as millions of Africans were forcibly transported to work sugar plantations. The sugar that sweetened European tea and coffee came at an immeasurable human cost. The plantation system developed for sugar production would later be applied to coffee, cotton, and tobacco, shaping the economic and social development of the Americas for centuries. Coffee spread from its origins in Ethiopia throughout the tropical world. By the 18th century, coffee plantations operated in Yemen, Java, the Caribbean, and Brazil. Coffee required specific conditions: altitude, temperature, rainfall. It grew on hillsides where other crops struggled. Coffee became a global commodity. Its production concentrated in tropical regions, while consumption occurred primarily in temperate zones. This geographic separation between production and consumption became characteristic of industrial age agriculture, where crops increasingly moved long distances from farm to table. The biological exchanges initiated during this period continued and accelerated. By the 19th century, botanists and colonial administrators actively sought out crops that might thrive in new environments. Rubber trees from Brazil were transplanted to Southeast Asia. Cinchonai trees, source of quinine, moved from South America to plantations in India and Java. Tea cultivation spread from China to India, Ceylon, and Africa. Each transfer required experimentation, adaptation, and often failure before success. But the successes reshaped global agriculture, creating new centres of production for crops far from their origins, and binding the world's agricultural systems into an increasingly interconnected network. The transformation of agriculture accelerated dramatically during the 18th and 19th centuries, particularly in Britain and later across Europe and North America. This period, often called the Agricultural Revolution, saw the replacement of traditional farming methods with new techniques, new crops, and new understandings of plant and animal biology. The changes were not a sudden revolution in the political sense, but rather a gradual intensification of agricultural productivity that made possible the later Industrial Revolution by freeing labour from farms and increasing food supplies for growing urban populations. The enclosure movement in Britain fundamentally altered rural landscapes and farming practices. For centuries, much of England's agricultural land had been organised into open field systems, where individual farmers worked scattered strips within large common fields. Villagers shared grazing rights on common pastures. This system had persisted since medieval times, but it became increasingly incompatible with new agricultural techniques that required consolidated holdings and long-term investment in land improvement. Between the 16th and 19th centuries, through both gradual agreement and parliamentary acts, these open fields were enclosed, divided into separate farms surrounded by hedges or walls. Enclosure allowed individual farmers to implement improvements without requiring community consensus, but it also displaced many small farmers and landless labourers who had depended on common land for survival. On these newly consolidated farms, progressive landowners experimented with innovations that would spread across the agricultural world. The Norfolk four-course rotation became widely adopted in regions with similar climates. This system rotated wheat, turnips, barley, and clover across 4 fields over 4 years. Unlike earlier 3-field systems that left land fallow, the Norfolk rotation kept all land productive. Turnips, planted in the field that would have been fallow, provided winter fodder for livestock. Clover, a legume, fixed nitrogen in the soil while also feeding animals. The system integrated crop and animal farming more tightly than before. More animals could be kept through winter, producing more manure, which fertilized the fields, increasing crop yields. higher yields supported more animals in a virtuous cycle of intensification. Selective breeding of livestock accelerated during this period. Robert Bakewell, an English farmer in the 18th century, pioneered systematic breeding programs for sheep and cattle. Previous breeding had been haphazard, with animals mating randomly or according to availability. Bakewell carefully selected animals with desired traits and prevented random mating, achieving dramatic improvements in meat production. His Leicester sheep produced more meat on less feed than traditional breeds. His Longhorn cattle grew larger and faster. Other breeders applied similar principles to different species, developing specialized breeds for specific purposes. Dairy cattle that produced more milk, beef cattle that grew larger, sheep with finer wool or better meat. The same principles applied to plant breeding, though understanding of heredity remained primitive. Farmers had always saved seeds from their best plants, but 18th and 19th century plant breeders approached this more systematically. They made deliberate crosses between varieties, selected offspring with desired characteristics, and repeated the process across generations. Wheat varieties emerged that resisted disease better, produced larger grains, or matured faster. Potato breeders developed varieties suited to different soils and climates. Each improvement was the result of careful observation and systematic selection, accomplished without any understanding of genetics or DNA. New crops entered European rotations during this period, most importantly the potato and maize from the Americas. The potato particularly transformed agriculture in northern and eastern Europe. It thrived in climates too cold or wet for reliable grain production. A family could survive on a much smaller plot of land when growing potatoes than when growing grain. This allowed populations to expand into previously marginal areas and supported overall population growth. The potato's importance made its vulnerability dangerous, as the Irish famine would demonstrate, but before that catastrophe, it enabled demographic expansion that would have been impossible otherwise. Agricultural machinery began to transform fieldwork. The seed drill, refined by Jethro Tull in the early 18th century, planted seeds in neat rows at controlled depths, and spacing rather than scattering them broadcast across the field. This improved germination rates, reduced seed waste, and made weeding easier since the rows of crops were distinguishable from weeds growing between them. Threshing machines, developed in the late 18th century, separated grain from stalks mechanically rather than through hand flailing, reducing labour requirements and speeding harvest processing. These machines were expensive and primarily adopted by larger farms, but they demonstrated agriculture's potential for mechanisation. The scientific understanding of plant nutrition advanced significantly during the 19th century. For thousands of years, farmers had known that manure and certain crops improved soil fertility, but they did not understand why. In 1840, Justus von Liebig, a German chemist, published research explaining that plants required specific mineral nutrients, particularly nitrogen, phosphorus, and potassium. He demonstrated that these nutrients could be supplied through chemical fertilizers rather than only through organic sources like manure or compost. This insight would eventually transform agriculture, though the full impact would not be felt until the 20th century, when industrial production of synthetic fertilizers became economically viable. Guano, bird droppings accumulated over centuries on islands off the coast of Peru and Chile, became an important fertilizer during the mid-19th century. Rich in nitrogen and phosphorus, guano dramatically increased crop yields when applied to fields. European and North American farmers imported vast quantities, stripping island deposits that had accumulated over millennia. The guano trade became economically significant enough to provoke diplomatic disputes and military conflicts. When easily accessible guano deposits were exhausted, attention turned to mineral sources of phosphorus and potassium, and to finding ways to fix atmospheric nitrogen chemically. Drainage systems improved dramatically with the development of clay tile drains in the mid-19th century. Waterlogged soils had always limited agriculture in areas with high rainfall or poor natural drainage. Previous drainage methods involved digging open ditches, which took up land, required constant maintenance, and interfered with farm work. Clay tile drains, laid underground, carried excess water away without occupying surface space or creating obstacles to ploughing and harvesting. This technology opened vast areas of previously marginal land to productive agriculture, particularly in Britain, the Netherlands, and the American Midwest. Transportation improvements paralleled agricultural intensification. Canals and later railways reduced the cost of moving agricultural products from farms to urban markets. This connectivity allowed regional specialization, with different areas focusing on crops or livestock best suited to local conditions while importing products more efficiently produced elsewhere. British farms increasingly focused on meat and dairy production, importing grain from abroad. This geographic division of agricultural labour increased overall efficiency, but also created dependencies that would prove significant during times of international conflict or trade disruption. Agriculture was becoming a system that functioned at regional and global scales, not merely at the level of individual farms or local communities. The mechanization of agriculture transformed farming from a labour-intensive enterprise conducted primarily through human and animal muscle power into an increasingly mechanized industry. This transition occurred unevenly across the world, beginning in wealthy nations during the 19th century and accelerating dramatically in the 20th. The social consequences were as profound as the technical ones, as millions of farm workers left the land for cities, and the relationship between farmer, soil, and crop fundamentally changed. The reaper, invented by Cyrus McCormick in the 1830s, demonstrated mechanization's potential. Before mechanical reapers, harvesting grain required teams of workers with scythes or sickles, cutting stalks by hand in back-breaking labour that had to be completed quickly before grain shattered and fell to the ground. McCormick's machine, pulled by horses, cut grain with mechanical blades and collected it on a platform for bundling. One machine with a single operator could harvest as much in a day as a dozen workers with hand tools. The reaper spread rapidly across American wheat farms, where labour was scarce and land abundant. In Europe, where farms were smaller and labour more plentiful, adoption occurred more slowly. The combine harvester, developed in California in the 1880s, integrated cutting, threshing and cleaning into a single operation. Early combines were enormous machines pulled by teams of 20 or more horses or mules. They could harvest and process 50 acres of wheat in a single day, work that would have required hundreds of labourers. The scale of these machines matched the scale of Western American agriculture, where farms of thousands of acres were becoming common. As internal combustion engines replaced horses in the early 20th century, combines became more powerful and efficient. Self-propelled combines appeared in the 1920s, eliminating the need for draft animals entirely. The tractor revolutionized farm power. Early tractors appeared in the 1890s, powered by steam engines. These machines were massive, expensive, and practical only on the largest farms. Gasoline-powered tractors, lighter and more versatile, became commercially viable in the early 1900s. Henry Ford's Fordson tractor, introduced in 1917, brought mass production techniques to agricultural equipment, dramatically reducing costs. By the 1930s, tractors were replacing horses and mules on farms across the developed world. The transition freed land previously used for growing animal feed, making it available for human food production. It also eliminated the daily labour of caring for draft animals and reduced the skill required for certain farm tasks. A tractor driver needed different knowledge than a teamster managing horses, and some of the intimate connection between farmer and animal was lost in the exchange. Mechanisation extended beyond harvest and tillage. Mechanical corn pickers, cotton pickers, potato diggers, and hay balers appeared throughout the early 20th century, each eliminating jobs that had previously required significant human labour. The cotton picker particularly transformed Southern American agriculture. Cotton harvesting had remained stubbornly resistant to mechanisation because the bolls opened at different times and required selective picking. Mechanical pickers that worked reliably did not appear until the 1940s. Their adoption accelerated the great migration of African Americans from southern farms to northern cities, as millions of agricultural workers found their labour no longer needed. The application of chemical fertilizers industrialized plant nutrition. In 1909, Fritz Haber, a German chemist, developed a process for synthesizing ammonia from atmospheric nitrogen. This Haber-Bosch process, scaled up for industrial production, solved the nitrogen limitation that had constrained agriculture for millennia. Previously, nitrogen came from manure, compost, crop rotation with legumes, or limited mineral sources like Chilean nitrates. These sources could not supply enough nitrogen for intensive agriculture at the scale industrial societies demanded. Synthetic ammonia fertilizer changed this completely. Farmers could apply nitrogen in quantities that would have been impossible through organic sources. Yields increased dramatically. A bushel of wheat that required an acre of land in 1900 could be produced on a third of an acre by the mid-20th century, partly because of synthetic fertilizer. The widespread adoption of chemical fertilizers had consequences beyond increased yields. It reduced the necessity for crop rotation and animal integration. Farmers could grow grain continuously on the same land by applying synthetic nitrogen rather than rotating with legumes or relying on manure. This simplified farming in some ways, but eliminated the ecological benefits of diverse rotations. Soil organic matter declined. Beneficial organisms that thrived in varied cropping systems diminished. The practice of agriculture became more divorced from ecological principles and more dependent on external industrial inputs. Chemical pesticides followed a similar trajectory. Farmers had always battled insects, fungi, and weeds, using methods ranging from hand removal to applications of sulfur, arsenic compounds, or botanical extracts. These controls were marginally effective at best. Modern synthetic pesticides, beginning with DDT in the 1940s, promised complete control. DDT killed insects effectively and initially appeared safe for humans and wildlife. It became widely used in agriculture and public health. Other synthetic pesticides followed. Herbicides that killed weeds, fungicides that prevented crop diseases, insecticides targeting specific pests. These chemicals increased yields by reducing crop losses, but their environmental impacts would later prove severe. Irrigation expanded massively during the 20th century, enabled by electric pumps and large-scale water projects. In the American West, enormous dams on the Colorado, Columbia, and other rivers created reservoirs that supplied water to millions of acres of farmland. Deep wells tapping ancient aquifers, pumped by electric motors, transformed regions like the Great Plains into productive cropland. In India, China, and elsewhere, similar expansions brought irrigation to areas that had practiced only rain-fed agriculture. This expansion supported growing populations, but also created new vulnerabilities. Aquifer depletion accelerated in many regions as pumping exceeded natural recharge. Rivers that once reached the sea now dried up before their mouths. Soil salinization affected millions of acres of irrigated land. Hybrid crops represented another major innovation. Breeders discovered that crossing carefully selected parent lines produced hybrid offspring with superior characteristics, a phenomenon called hybrid vigor. Hybrid corn, commercialized in the 1930s, yielded significantly more than traditional open-pollinated varieties. But hybrid seeds had to be purchased new each year since second-generation seeds did not maintain the desirable characteristics. This created ongoing markets for seed companies and made farmers dependent on commercial seed rather than saving their own. The hybrid approach later extended to other crops, increasing yields but also changing the economics of farming. The transformation of agriculture during this period increased productivity to levels unimaginable to earlier generations. A single farmer in 1950 could feed many more people than a farmer in 1900. But this productivity came with costs: dependence on fossil fuels for machinery and fertilizer production, environmental damage from chemicals and irrigation, loss of soil health, displacement of farm workers, and consolidation of farms into larger industrial operations. Agriculture had become vastly more productive, but also more fragile, dependent on continuous inputs of energy and chemicals, and increasingly vulnerable to supply disruptions or environmental limits. The Green Revolution of the mid-20th century represented one of the most dramatic increases in agricultural productivity in human history. Beginning in the 1940s and reaching its full impact by the 1970s, this transformation centered on the development and dissemination of high-yielding crop varieties, particularly wheat and rice, combined with intensive use of irrigation, fertilizers, and pesticides. The revolution prevented predicted famines and allowed populations to grow in regions that had struggled with food security, but it also created new dependencies and environmental challenges whose full costs would only become apparent decades later. Norman Borlaug, an American agronomist working in Mexico, pioneered the development of semi-dwarf wheat varieties that became central to the Green Revolution. Traditional wheat varieties grew tall, and when farmers applied fertilizer to increase yields, the plants often grew so tall and grain-heavy that they fell over or lodged before harvest. Borlaug bred wheat varieties with shorter, stronger stalks that could support heavy grain heads without lodging. These semi-dwarf varieties responded dramatically to fertilizer application, producing yields double or triple those of traditional wheat. When combined with adequate water, fertilizer, and pest control, the new varieties transformed wheat production in Mexico and later in India, Pakistan, and other developing nations. Rice underwent similar transformation. Scientists at the International Rice Research Institute in the Philippines developed IR-8, a semi-dwarf rice variety released in 1966. Like Borlaug's wheat, IR-8 had short, sturdy stalks that resisted lodging and responded well to fertilization. It also matured faster than traditional varieties, allowing multiple crops per year in tropical climates with year-round growing seasons. IR-8 and subsequent improved varieties spread across Asia, dramatically increasing rice production. Countries that had imported grain became exporters within a decade. The success of these varieties depended on more than just genetics. They required irrigation to ensure adequate water throughout the growing season. They needed fertilizer, particularly nitrogen, in quantities far exceeding what organic sources could provide. They were vulnerable to pests and diseases, necessitating pesticide applications, and they demanded precise management, with farmers timing planting, irrigation, fertilization, and harvest according to schedules more rigid than traditional farming required. The entire package of inputs and practices had to be adopted together for the system to work. Partial adoption often failed. Governments in developing countries, recognizing the potential to increase food security and avoid dependence on imports, actively promoted green revolution technologies. They subsidized fertilizers and pesticides, invested in irrigation infrastructure, provided credit for farmers to purchase inputs, and established extension services to teach new techniques. In India, government support for green revolution agriculture was explicit and comprehensive. The country had experienced severe famines in the 1940s and faced predictions of worse food shortages as population growth accelerated. The adoption of high-yielding varieties, supported by substantial public investment, transformed India from a grain importer to self-sufficiency and eventually to a position of surplus production. The Green Revolution's impact on global food security was substantial. World grain production doubled between 1960 and 2000, while population grew from 3 billion to 6 billion. Without the yield increases from improved varieties and intensive management, feeding the growing population would have required either massive expansion of agricultural land, likely at the expense of forests and natural ecosystems, or widespread famine. The Green Revolution, whatever its limitations and costs, prevented catastrophic food shortages that many experts had considered inevitable. However, the benefits distributed unevenly. Wealthier farmers who could afford inputs and had access to irrigation adopted the new technologies first and gained the most. Poorer farmers, particularly those without irrigation or capital for inputs, often could not participate or fell behind as grain prices declined due to increased supply. This widened economic inequality within rural communities. In some regions, small farmers sold their land to larger operators, who could farm more intensively. The Green Revolution contributed to rural consolidation and the growth of larger, more commercialized farms at the expense of subsistence agriculture. Environmental costs became increasingly apparent as Green Revolution agriculture matured. Intensive use of nitrogen fertilizer led to nutrient runoff that polluted rivers, lakes, and coastal waters. Algae blooms fueled by agricultural runoff created dead zones in water bodies worldwide. Pesticide use harmed beneficial insects, contaminated water supplies, and in some cases poisoned farm workers. The monoculture approach, growing vast areas of genetically uniform crops, increased vulnerability to pests and diseases. When a pest or pathogen could attack the crop, it spread rapidly across regions planted with the same variety. This required even more pesticide use in a cycle that some observers compared to an agricultural treadmill, where farmers had to run faster just to stay in place. Soil degradation became a concern in intensively farmed regions. Continuous cropping without adequate organic matter inputs depleted soil structure. Erosion accelerated on land where crop residues were removed rather than returned to the soil. Irrigation without proper drainage caused salinization. Some of the most productive Green Revolution regions began showing signs of declining yields by the 1990s, suggesting that the initial productivity gains might not be sustainable indefinitely without addressing underlying soil health issues. Water consumption for irrigation increased enormously as Green Revolution agriculture expanded. Aquifers that had accumulated water over thousands of years were depleted within decades. In northwestern India, groundwater levels fell by meters per year as millions of tube wells pumped water for intensive wheat and rice production. The Ogallala Aquifer, beneath the American Great Plains, though not directly part of the Green Revolution, experienced similar depletion from intensive irrigation. Rivers were diverted so completely for agricultural use that some, like the Colorado in North America and the Yellow River in China, regularly failed to reach the sea. The Aral Sea in Central Asia shrank to a fraction of its former size as water from its tributary rivers was diverted for cotton irrigation, creating an environmental catastrophe. The Green Revolution also created social changes beyond economics and environment. Traditional farming knowledge, accumulated over generations, became less relevant when replaced by standardized packages of practices and inputs. Farmers who had been experts in their local conditions found themselves dependent on external advisors and commercial suppliers. The diversity of crop varieties that had been maintained by traditional farmers declined as uniform high-yielding varieties displaced local land races. This loss of genetic diversity reduced the reservoir of traits that future breeders might need to develop varieties resistant to new pests, diseases, or changing climates. Despite these costs, the Green Revolution demonstrated that agricultural productivity could be dramatically increased through the systematic application of science and technology. It showed that famine was not inevitable, that human ingenuity could respond to the challenge of feeding growing populations. But it also revealed that productivity gains alone were insufficient, that questions of equity, sustainability, and environmental impact had to be addressed alongside yield increases. These lessons would inform debates about agricultural development in subsequent decades, as attention turned to whether the Green Revolution's approach could or should be extended, modified, or fundamentally rethought. As the limitations of industrial agriculture became increasingly apparent during the late 20th century, alternative approaches emerged that sought to maintain productivity while reducing environmental damage and restoring ecological balance. These movements, ranging from organic farming to integrated pest management to conservation agriculture, represented both a critique of conventional practices and an attempt to develop farming systems that could sustain productivity indefinitely rather than mining soil and water resources for short-term gains. Organic farming, though practiced in various forms throughout history, crystallized as a distinct movement in the early to mid-20th century. Pioneers like Albert Howard in India, Rudolf Steiner in Europe, and J.I. Rodal in America advocated farming systems that worked with natural processes rather than attempting to override them with synthetic inputs. Organic principles emphasized building soil health through compost and cover crops, controlling pests through biological methods and crop diversity rather than chemicals, and maintaining closed nutrient cycles where waste from one part of the farm fed another part. These ideas gained little traction initially, dismissed by mainstream agriculture as impractical nostalgia for pre-industrial methods. The environmental movement of the 1960s and 70s, catalyzed partly by Rachel Carson's 1962 book Silent Spring, documenting pesticide damage to wildlife, created new interest in organic farming. Consumer concern about pesticide residues in food grew. Studies revealed that synthetic pesticides persisted in the environment, accumulated in food chains, and harmed non-target organisms, including beneficial insects and birds. DDT, once considered a miracle chemical, was banned in many countries after evidence showed it caused eggshell thinning in predatory birds, driving some species toward extinction. This recognition that chemicals considered safe could have unforeseen long-term consequences made organic farming's precautionary approach more appealing. Organic agriculture expanded significantly beginning in the 1980s. Standards and certification systems developed to define what qualified as organic production. These systems prohibited synthetic pesticides and fertilizers while requiring specific practices for soil management, pest control, and animal welfare. Organic farms typically use crop rotation, cover crops, compost, and mechanical weed control. They accepted lower yields compared to conventional farming, but often achieved better profitability through premium prices consumers paid for organic products. Research gradually demonstrated that organic farming could approach conventional yields for many crops when farmers gained experience with the methods and when comparing farms over multiple years, rather than single growing seasons. The debate over organic farming's productivity and sustainability remained contentious. Critics argued that organic agriculture could not feed the world's growing population because of lower yields and the large land area required. They pointed out that organic farming often relied on inputs like bone meal or fish emulsion that ultimately derived from industrial agriculture or fishing. Supporters countered that conventional agriculture's dependence on fossil fuels and its environmental damage made it ultimately unsustainable, and that organic methods built soil health over time while conventional methods depleted it. Both sides had valid points. Neither system was without limitations. Integrated pest management offered a middle path between organic and conventional approaches. Rather than attempting to eliminate all pests, integrated pest management recognized that some pest presence was inevitable and tolerable. Farmers monitored pest populations, intervened only when pests exceeded economic thresholds, and used the least disruptive control methods available. This might mean tolerating low levels of insect damage, using targeted pesticide applications only when necessary rather than on preventive schedules, encouraging beneficial insects that preyed on pests, or selecting pest-resistant crop varieties. Integrated pest management reduced pesticide use substantially while maintaining yields close to conventional levels. Many government agricultural services and large-scale commercial farms adopted integrated pest management principles during the late 20th century. Conservation agriculture emerged as another alternative approach, focusing particularly on soil health and erosion control. The core principles included minimal soil disturbance through reduced or no-till farming, permanent soil cover through crop residues or cover crops, and diverse crop rotations. No-till farming, where seeds were planted directly into soil without ploughing, contradicted conventional wisdom that soil must be turned and pulverized for good crop growth. Yet research showed that undisturbed soil maintained better structure, retained more organic matter, held water more effectively, and eroded far less than ploughed soil. The crop residues left on the surface protected soil from rain impact and wind, reduced evaporation, and provided habitat for beneficial organisms. No-till farming required different equipment and management approaches. Specialized planters could cut through crop residue and place seeds at the correct depth. Herbicides, particularly glyphosate, became important for controlling weeds that would previously have been buried by ploughing. This reliance on herbicides troubled some observers who saw conservation agriculture trading one environmental problem for another. However, the soil health benefits were substantial. Farms practicing no-till for many years developed rich, biologically active soils with increased carbon content, improved water infiltration, and enhanced resilience to drought. Cover crops gained renewed attention as farmers recognized their multiple benefits. A cover crop, planted between cash crops to cover otherwise bare soil, prevented erosion, suppressed weeds, and added organic matter when terminated and left on the surface or incorporated into soil. Legume cover crops fixed nitrogen, reducing fertilizer requirements. Deep-rooted cover crops brought nutrients from lower soil layers to the surface. Winter cover crops protected soil through cold months when erosion risk was highest. Integrating cover crops into rotations required careful management to avoid delays in planting the subsequent cash crop, but farmers who mastered the practice often found their soils improved noticeably over several years. Agroforestry, the integration of trees with crops or livestock, represented another approach that gained traction in tropical regions particularly. Trees provided shade for crops or animals, prevented erosion on slopes, created habitat for beneficial insects and birds, and produced additional products like fruit, nuts, or wood. In coffee and cacao production, shade-grown systems mimicked forest structure while producing marketable crops. In Africa, farmers intercropped with nitrogen-fixing trees that improved soil while providing fodder and firewood. These systems were more complex to manage than monocultures, but created more resilient and diverse agricultural landscapes. Precision agriculture emerged as industrial farming's answer to environmental concerns. Using GPS-guided equipment, soil sensors, drones, and computer analysis, precision agriculture aimed to apply inputs exactly where and when needed, rather than uniformly across entire fields. Variable rate fertilizer applicators adjusted rates based on soil tests for different zones within a field. Precision irrigation systems delivered water only to plants showing moisture stress. This approach reduced input costs while minimizing environmental impact from excess fertilizer or water. It represented high-tech industrial agriculture, attempting to become more efficient and environmentally responsible without abandoning its fundamental approach. These various alternative and reformed approaches to agriculture shared a recognition that farming methods developed during the mid-20th century, while enormously productive, had created unsustainable dependencies and environmental damage. Whether the future belonged to organic systems, conservation agriculture, precision farming, or some synthesis of these approaches remained uncertain. What seemed clear was that agriculture could not continue indefinitely on the trajectory of ever-increasing chemical and energy inputs applied to biologically simplified systems. The question was not whether agriculture would change, but how quickly and in what direction. The ability to directly modify plant genetics, rather than relying on traditional breeding's slower selection processes, emerged as one of the most consequential and controversial agricultural developments of the late 20th and early 21st centuries. Genetic engineering allowed scientists to insert specific genes from one organism into another, creating combinations that could never occur through natural reproduction or conventional breeding. This technology promised crops with enhanced nutrition, built-in pest resistance, and tolerance to environmental stresses, but it also raised concerns about unintended ecological consequences, corporate control of agriculture, and the ethics of manipulating life at its most fundamental level. The first genetically modified crops approved for commercial cultivation appeared in the mid-1990s. Bt corn and Bt cotton contain genes from Bacillus thuringiensis, a soil bacterium that produces proteins toxic to certain insects. Plants expressing these Bt proteins manufactured their own insecticide, killing pests that fed on them. This dramatically reduced the need for insecticide sprays, benefiting both farmers' economics and environmental health. Studies showed that Bt cotton reduced insecticide applications by 50 to 70% in many regions, decreasing farmer exposure to toxic chemicals and reducing harm to beneficial insects. Herbicide-tolerant crops represented another major category of genetic modification. Crops engineered to resist glyphosate, a broad-spectrum herbicide, allowed farmers to spray entire fields to kill weeds without harming the crop. This simplified weed management and supported no-till farming practices by providing an alternative to mechanical weed control through ploughing. Herbicide-tolerant soybeans, corn, cotton, and canola became widely adopted in North and South America. By the early 2000s, the majority of soybeans and cotton grown in the United States were genetically modified varieties. The adoption of genetically modified crops occurred rapidly in some countries while facing fierce resistance in others. The United States, Canada, Brazil, and Argentina embraced the technology with relatively minimal regulation. Farmers in these countries adopted genetically modified varieties at extraordinary rates, driven by economic benefits and reduced labour requirements. In contrast, the European Union imposed strict regulations on genetically modified crop cultivation and labelling, reflecting public concern about food safety and environmental risks. This regulatory divide created trade tensions and contributed to a global debate about appropriate oversight of agricultural biotechnology. Opposition to genetically modified crops came from multiple directions. Environmental groups worried about unintended ecological consequences, such as the possibility of engineered genes spreading to wild relatives of crops or resistant weeds, and insects evolving in response to continuous exposure to Bt proteins or herbicides. These concerns proved partly justified. By the 2010s, glyphosate-resistant weeds had become widespread in areas with intensive herbicide-tolerant crop cultivation, forcing farmers to use additional herbicides or return to mechanical weed control. Some insect populations developed resistance to Bt proteins, requiring farmers to implement refuge strategies where sections of fields were planted with non-Bt varieties to maintain populations of susceptible insects. Consumer advocacy groups questioned the safety of genetically modified foods, though scientific consensus held that approved genetically modified crops were as safe to eat as conventional varieties. The concern was less about proven harm than about unknown long-term effects and the inadequacy of testing protocols. Critics pointed out that genetic modification could have unpredicted effects beyond the intended trait, potentially creating novel allergens or altering nutritional profiles in unintended ways. The scientific community largely dismissed these concerns as unsupported by evidence, but the gap between expert opinion and public perception remained substantial in many regions. The economics and politics of genetically modified crops generated perhaps the deepest controversies. Most genetically modified varieties were developed and sold by large corporations that held patents on the genes and traits. Farmers who planted these varieties had to sign agreements not to save seeds for replanting, requiring them to purchase new seeds each season. Critics argued this gave corporations unprecedented control over the food system and created dependency relationships that disadvantaged farmers, particularly small-scale farmers, in developing countries. Supporters countered that seed saving had already become rare for many crops due to hybrid varieties, and that patent protections incentivized the research investments needed to develop improved varieties. The debate intensified when considering genetically modified crops in developing countries. Golden rice, engineered to produce beta-carotene and address vitamin A deficiency, which caused blindness and death in hundreds of thousands of children annually, became a symbolic battleground. Proponents saw it as a humanitarian application of biotechnology to address malnutrition. Opponents viewed it as a distraction from more fundamental solutions to poverty and dietary diversity, and worried it would normalize genetic modification and corporate control in subsistence agriculture. The rice's deployment was delayed for years by regulatory hurdles and organized opposition, illustrating how technical solutions to agricultural problems could not be separated from political and social contexts. Beyond insect resistance and herbicide tolerance, genetic engineering opened possibilities for more ambitious modifications. Drought-tolerant crops containing genes that helped plants maintain function under water stress offered potential for agriculture in arid regions or under changing climate conditions. Crops with enhanced nitrogen use efficiency could reduce fertilizer requirements. Plants engineered to produce pharmaceuticals or industrial chemicals could turn farms into biological factories. Perennial grain crops, if they could be developed, might combine the productivity of annual crops with the soil-building properties of perennial plants. Some of these advances remained in research phases, while others moved toward commercialization. Gene editing technologies, particularly CRISPR-Cas9, developed in the 2010s, provided more precise genetic modification tools than earlier techniques. CRISPR allowed scientists to make specific changes to an organism's existing genes rather than inserting foreign genes. This precision reduced concerns about unintended modifications and blurred the distinction between genetic engineering and traditional breeding. Some regulatory frameworks treated gene-edited crops differently from transgenic crops containing foreign genes, though debates continued about whether this distinction was scientifically meaningful. Gene editing accelerated the pace of crop development, allowing changes that would take years or decades through traditional breeding to be accomplished in months. The trajectory of agricultural biotechnology seemed likely to continue despite controversies. The techniques were too powerful and the potential benefits too significant for research to stop. Climate change created new urgency for developing crops that could tolerate heat, drought, flooding, and salinity. Growing populations required continued productivity increases. Reducing agriculture's environmental footprint demanded crops that needed fewer inputs while maintaining yields. Genetic modification offered tools to address these challenges more rapidly than traditional methods allowed. Yet the technology's implementation would continue to be shaped not just by scientific capability, but by public acceptance, regulatory frameworks, corporate interests, and ethical considerations. The future of genetically modified crops depended as much on social and political factors as on continued technical advances. Agriculture stands at a crossroads in the early 21st century, facing challenges unprecedented in scale and urgency. Climate change disrupts weather patterns that farmers have relied upon for generations. Population growth continues, though at a slowing rate, with projections suggesting nearly 10 billion people by mid-century. Soil degradation affects a third of the world's agricultural land. Water scarcity intensifies in regions that produce much of the global food supply. Biodiversity loss threatens the ecosystems that agriculture depends upon for pollination, pest control, and nutrient cycling. Meeting these challenges requires innovations in farming technology and practice, but also fundamental reconsiderations of how societies produce and consume food. Vertical farming represents one radical reimagining of agricultural space. Rather than spreading crops across vast horizontal expanses of land, vertical farms stack production layers in controlled indoor environments. LED lighting provides precisely calibrated wavelengths for photosynthesis. Hydroponic or aeroponic systems deliver water and nutrients directly to plant roots without soil. Climate control maintains optimal temperature and humidity. This approach eliminates weather uncertainty, allows production in cities near consumers, uses a fraction of the water required for field agriculture, and permits year-round harvests regardless of season. Several vertical farms operate commercially, growing lettuce, herbs, and other high-value crops in urban warehouses and shipping containers. Yet vertical farming faces significant limitations. The energy required for artificial lighting is substantial, making the approach economically viable only for crops with high market value and in locations with cheap electricity, preferably from renewable sources. Staple crops like wheat, rice, or corn cannot be grown economically in vertical systems with current technology. The infrastructure costs are enormous, limiting expansion. Vertical farming may complement traditional agriculture by producing certain crops more efficiently in specific contexts, but it cannot replace field agriculture for feeding billions of people. It represents innovation at the margins rather than transformation at the core. Precision agriculture continues to advance, incorporating increasingly sophisticated sensors, data analysis, and automated equipment. Drones map field conditions, identifying areas of stress, disease, or nutrient deficiency invisible to ground-level observation. Soil sensors provide real-time data on moisture, temperature, and nutrient levels. Machine learning algorithms process this information to optimize irrigation, fertilization, and pest management decisions. Autonomous tractors and harvesters operate with minimal human supervision, guided by GPS and computer vision. This technology promises to make industrial agriculture more efficient and less wasteful, applying inputs only where needed and reducing environmental impact while maintaining or increasing yields. The challenge with precision agriculture lies in accessibility. The technology requires substantial capital investment, sophisticated technical knowledge, and often reliable internet connectivity for data processing and equipment control. Wealthy commercial farms in developed countries can implement these systems. Small-scale farmers in developing countries, who produce much of the world's food, generally cannot. This creates a risk of widening the gap between agricultural haves and have-nots, concentrating production and profit among large operations while marginalizing smallholders. Making precision agriculture techniques accessible and affordable for diverse farming contexts remains an unsolved problem. Regenerative agriculture has emerged as a framework attempting to go beyond sustainability to actual improvement of agricultural ecosystems. Where sustainable agriculture aims to maintain productivity indefinitely, without degradation, regenerative agriculture seeks to restore soil health, enhance biodiversity, and sequester atmospheric carbon in soil. Practices include no-till farming, diverse cover crops, integrated livestock grazing, and elimination of synthetic inputs. Proponents argue that properly managed regenerative systems can produce adequate yields while building soil organic matter, improving water retention, and creating habitats for wildlife. The approach has gained attention from environmental advocates and some food companies seeking to reduce their carbon footprints. Critics question whether regenerative agriculture can scale sufficiently to feed global populations without expanding agricultural land into remaining forests and grasslands. Yields from regenerative farms are often lower initially, though some improve over time as soils recover. The transition period requires farmers to accept reduced income while learning new techniques and waiting for soil improvement. Without support systems to help farmers through this transition, widespread adoption seems unlikely. The debate mirrors earlier arguments about organic farming, with similar tensions between idealized goals and practical economics. Climate adaptation has become essential regardless of farming approach. Temperature increases, shifting precipitation patterns, and more frequent extreme weather events force adjustments to crop choices, planting dates, and management practices. Plant breeders work to develop varieties tolerant to heat, drought, and flooding. Farmers experiment with crops previously unsuited to their regions as temperature zones shift. Irrigation systems require redesign to cope with changing water availability. Risk management through crop insurance and diversification becomes more critical as weather becomes less predictable. These adaptations occur incrementally across millions of farms, a distributed response to global change. Alternative proteins from plant-based substitutes or cellular agriculture may eventually reduce agriculture's environmental footprint by decreasing demand for livestock production. Livestock, particularly cattle, require vast land areas for grazing and feed production, produce significant greenhouse gas emissions, and consume large quantities of water. If synthetic meats or plant-based alternatives could replicate the taste, texture, and nutrition of animal products while using fewer resources, they might substantially reduce pressure on agricultural systems. Several companies have developed plant-based meat substitutes gaining market acceptance. laboratory-grown meat from cultured animal cells has achieved technical feasibility, though economic viability and regulatory approval remain uncertain. Whether these alternatives will substantially displace conventional livestock production or remain niche products depends on continued technical improvement, consumer acceptance, and relative costs. Urban agriculture, community gardens, and local food systems represent another dimension of agricultural evolution. While unlikely to provide most people's calories, these initiatives reconnect urban populations with food production, reduce transportation distances, and create green spaces in cities. Rooftop farms, vacant lot gardens, and community-supported agriculture programs demonstrate that food production need not be entirely separated from population centres. These small-scale efforts may contribute more to social and educational goals than to overall food security, but they maintain agricultural knowledge and practice in populations increasingly distanced from farming. The future of agriculture will likely involve combinations of approaches rather than a single solution. Industrial farms deploying precision technology will coexist with regenerative operations, building soil health, and small-scale organic producers serving local markets. Vertical farms may grow salad greens in cities, while vast fields continue producing wheat and corn. Genetically modified crops and traditional varieties will both have roles. The challenge lies in ensuring that agricultural evolution addresses not just productivity, but also equity, environmental health, and resilience. 12,000 years after agriculture began, the essential questions remain. How do we produce enough food for everyone? How do we do so without destroying the ecosystems that sustain us? And how do we organise food systems fairly? The tools available to answer these questions have grown vastly more sophisticated, but the questions themselves persist, as fundamental now as they were when the first farmers planted their first seeds.